Alright, 3.3 is titled Specific Heat. And I'll start with a question. The pan, or the pot that you see on this page right here, it's an interesting pot. The bulk of it is made out of some type of silvery material, some type of silvery metal, maybe a stainless steel. But the bottom of it is made out of a different material. That material is probably, just by the looks of it, some type of copper, maybe brass, which has copper and zinc, but most likely the bulk of it is copper. So my question to you would be, why? Why go to such great lengths to make the pot out of two different materials, especially when this material will be considerably more expensive than that material? The answer lies in specific heat. So let's figure this out. Alright, let's take a look at the graph below. It shows the melting and boiling of water, and we've become familiar with these types of graphs, these types of energy transition graphs. So we know that heat's going to be added to the system, either it's on a stove or a Bunsen burner. So heat is being added to the system to do this particular process. But I think an interesting question to ask is, well, how much heat is being added? And maybe another question would be, can we measure heat? Can heat actually be measured? A third question might be, why do we care? Is it important to care about this? And I would suggest that, yes, it's very important to care because energy equals money. So if you're running a lab, you're going to want to make your processes as efficient as possible, use as little energy as possible, and thus save as much money as possible. So let's look at if we can measure heat. That's important. We have this term. It's called specific heat, right here. And it's defined as follows. It's the amount of heat that raises the temperature of 1 gram of a substance by 1 degree Celsius. So it's got to raise 1 gram of substance. So this is my substance, 1 gram. It's got to go from maybe 20 all the way to 21. And I can ask, question mark, how much heat is needed to do this? Okay. Now, every substance, whether it be this substance here, or maybe a red substance here, or maybe a green substance here, as long as I have 1 gram of substance, I can figure out how much heat is needed to raise that substance from 20 to 21 degrees Celsius. The interesting part is this number right here, the amount of heat needed, is going to be different for that material, it's going to be different for that material, and it's going to be different for that material right down there. Okay? Alright. So it's different for different substances. And we have certain units that we are going to use to be able to measure this thing called specific heat. And there are 2 of them that we got to be familiar with. The first one is called joules per gram degree Celsius. Now you're familiar with 2 of the units. This is called a compound unit. A compound unit has more than 1 unit in it. And you're familiar with 2 of the units. You obviously are familiar with grams, and you're familiar with degrees Celsius, but this guy might be a little bit new to you, the joule. The joule is a measurement of energy. So I go back to my previous slide which said, can heat be measured? Well, heat's just a flow of energy, so if we can measure energy, well, yeah, we should be able to measure heat. The other unit that's going to be of importance is this one, and it may be a bit more familiar to you. It's calories per gram degree Celsius. Oh, you're familiar with that number, that phrase right there, calories. You see in the back of your cereal box every morning, calories. But I want to make a note. The calorie that you see here, okay, the calorie that you see right there is a little bit different than the calorie on your box of cornflakes. This calorie equals 0.001 of the calories in your cereal, usually denoted with a capital C. So that means I need 1,000 of these guys, 1,000 of those guys, to make 1 dietary calorie. So an average dietary allowance for an average person is about 2,000 calories. That's actually 2 million physics calories or chemistry calories. So good thing we say 2,000 calories. All right. So let me give you some examples of specific heats of different materials. I said all materials can have different specific heats. All right, we've got aluminum on the top here, copper, gold, iron, silver, titanium, ammonium, ethanol, sodium chloride, and water. You don't have to memorize these. If you ever need these specific heats, I'll certainly provide them for you. But it's just kind of interesting to look at the values. Let's take a look, for instance, at the metals. Let's see, metal all the way down to here. Right? Okay, and then those are all metals. Okay, so these are metals. Okay, and then we have a couple of liquids, right? We have a liquid here, and a liquid here, and a liquid here. Then we have a solid. That's this guy. That's sodium chloride. So if we look at the liquids, we notice liquids have higher specific heats than metals do. It's interesting to think about why that would be. Okay, well, let's take a look over at the right side of the page here. If we have a match and we hold it underneath let's say we've got a little block of water. I don't know, we've got some type of block that holds water right here. And we have this another match, a totally identical match, and we hold it underneath a block of gold. And each one of these things are a kilogram in mass. Water is going to take about 30 times longer to heat than gold. So if I have my match underneath the piece of gold here, that gold is going to heat up from 20 degrees Celsius to 90 degrees Celsius pretty darn quick. But it will take 30 times longer to do that for the water. So if it took 1 minute for the gold to heat up, it will take 30 minutes for the water to heat up. That means it stores about 30 times more energy. So water stores a ton of energy. It's a great energy store. We benefit from that living close to Lake Michigan in the winter, although we really didn't see the effects of it this year. But it was really cold. Okay, so can we use these ideas? Can we use this idea of specific heat to figure out the amount of heat needed to warm up a particular sample to a particular temperature? Well, in fact, we can. Okay, first of all, heat in itself is just a measurement of calories or joules flowing into or out of a system. So when you're heating up your pot of noodles or your pot of water to cook noodles, you're transferring heat into the pot. You're transferring calories or joules into the pot. So in order to calculate those calories or joules, the amount of calories or joules that you're transferring into the pot, you need to know a couple of things. You need to know the change in temperature of the water inside the pot, the mass of the water inside the pot, and that letter right there, C, which is called the specific heat, and we just saw a chart on that on the previous slide. The amount of heat lost or gained by a substance is calculated from the three things: from the mass of the substance, notice in grams please, the temperature change, delta T, and that temperature change is going to be degrees Celsius or Kelvin. Okay, either of those two will work just fine. Degrees Fahrenheit will not. Don't use it. And letter C, specific heat of the substance. And the units for specific heat are kind of big, and I showed that on the previous slide. Again, calories per gram degree Celsius or joules per gram degree Celsius. The amount of energy needed to heat up 1 gram of substance 1 degree Celsius. All right, so that's our equation. Let's do some work with it now. Let's say we got a hot water bottle. It contains about 750 grams of water at 65 degrees Celsius. And we're using, if the water cools to body temperature, how many calories of heat could it be transferred to sore muscles? So we're saying we're taking this particular hot water bottle and you're putting it on like a sore muscle. And you're trying to alleviate the pain. And that heat is getting transferred to your muscle to alleviate soreness. Okay? When you get old like me, you'll figure out that this actually does happen. Okay, so our equation is this: Q equals M times C times delta T. And we do have some numbers that we can just kind of plug in. I hate plug and chug equations because sometimes they're meaningless and we don't get the value of them, but this is an important one. So you get 750 grams times the specific heat of what? Water. Okay, we need the specific heat of water, which, if you looked at that previous slide again, it's 1.00 calories per gram degree Celsius. And then the last thing that we'll need is that temperature change. So we went from 65 to 37. So what? That's 28 degrees Celsius, right? 28 degrees Celsius. Okay? So if we get that out of there, and we get the grams out of there, that looks good. We are left with what we're supposed to be left with, which is calories. And on our calculators, we'd punch in 750 times 1 times 28, and we should get out 21,000 calories. Okay, that's a huge number. So we could also report that like this. We could say 21 kilocalories, which are the same as food calories. So it'd be like 21 food calories, that much energy being transferred to your sore muscles. Okay? All right, now let's take a look at what happens when we're not just heating up a substance or cooling a substance down. What happens when we get to that point, when we actually heat a substance up so much that it boils and it starts to evaporate, or we cool it down so much that it actually starts to freeze? Obviously, we know that this is called a phase change, right? A change of phase. So how do things work in these cases? Well, I think it's obvious from our previous labs that when the phase starts changing, the temperature change equals 0. You remember that? So here's our graph. Okay, we had a plateau, increase, and a plateau. So right here, when we're melting, this is our melting portion, okay, right there. And here, when we're boiling, we have a temperature change of 0. Well, boy, if you think of our equation, Q equals mc delta T, it's not going to work because we know energy is being added. We know heat is being added. We see the Bunsen burner on. But if delta T is 0, then if you do your math, 0 times C times M is 0. 0 times anything is 0. 0 times 8 million is 0. 0 times a saber-toothed tiger is 0. So 0 times anything is 0. Okay, so it's not going to work. So we've done experiments with this, and we figured out a couple of things. First of all, figured out this number called the heat of fusion. Okay, the heat of fusion. That means that it takes 334 joules to go ahead and melt or freeze a sample of ice. And how big is that sample? 1 gram. Okay, 1 gram of ice. So if we're going to freeze ice, we need to remove 335 joules for every gram of water there is. If we're going to melt it, we have to put in 334 joules of energy. The other number, so that delta HF would be the value that corresponds to this point on the graph. The other number, delta HV, is the value that corresponds to that point in the graph. That's the heat of vaporization. Okay, look at, you need a whole bunch more energy in order to vaporize something to just freeze something. 2,260 joules per gram. So again, that's called the heat of vaporization. So at the plateaus, when we're trying to figure out, okay, how much energy is it going to take for me to go from this position all the way to that position, or from this position all the way to this position, how much energy is it going to take for me to do that? We have a new equation, and that is that the heat equals the mass of the sample, because obviously it's dependent upon the mass. The more stuff I have, the harder it is going to be to be able to heat it up. So it's the mass of the sample times delta HF. So that guy, let me go back here, is the heat of fusion. This guy would be the heat of vaporization. Okay, so this value pertains to that plateau, and this value pertains to that plateau right there. All right? So we're going to do some example problems right away at the beginning of class tomorrow to see how these things work, and then we'll start prepping for the lab. All right.